So far, we discussed greedy methods for approximating the solution of the P0 problem. We turn now to another breed of methods, relaxation-based algorithms. We are given a matrix A and a vector B, and our goal is to find the sparsest solution of the linear system AX equals B. We desire to achieve an approximation of this solution in reasonable time. And the path we take now is different from the greedy one we have discussed in length so far. Looking at the problem P0, it is yet another optimization task in which X is the unknown to be found. When it comes to continuous optimization tasks of this form, we seem to be well equipped with access to a rich theory and vast set of practical algorithms. So why not simply use these tools for the given problem? Well, this is not as easy as it may sound. P0 is a very challenging optimization problem since the L0 is a highly non-smooth function. This implies that P0 has many local minima points, and most of these are of no interest to us. What can we do? The answer is smoothing the L0 term, with the hope to simplify the problem while preserving its essence. This brings us to the family of relaxation algorithms. The L0 norm counts the number of non-zeros in a given vector x. This is done by applying an indicator function rho star on each of the entries in x, counting it as 0 if it is 0 and 1 otherwise. We will be interested in smoothing this function, and there are many ways to go about it. We shall propose several such smoothers so as to see what we are up against. Here are three smooth versions of the indicator function rho star, and these are commonly used in relaxing the L0 expression. The first is 1 minus a Gaussian curve. The second is x squared divided by alpha plus x squared. The third is simply absolute value of x to the power alpha. All these and many other options share something in common. As alpha tends to 0, these functions get closer and closer to the indicator function rho star. Here is a graph presenting these functions. Observe the relation between the color of the curves and the functions. Beyond smoothing the L0 function, another tool at our disposal is a graduated approximation, in which we start with a very wide smoothing and solve the problem, and then use a narrower option and recompute the solution, and so on. A progressive method such as this is expected to be able to overcome local minima traps. For example, consider the 1 minus Gaussian case. As alpha tends to 0, we get closer and closer to the rho star, and per each such option, we could recompute the solution and use it as a warm start for the next evaluation. Here is a block diagram of this method. Our objective function is alpha dependent, using the alpha smooth version of rho star. We initialize the algorithm with a very large alpha and solve the alpha smooth P0 problem. We proceed by decreasing alpha and repeating the process. However, a key step in this process is the use of the previous solution as an initialization to the next solver, a trick known by the name warm start. As we have already said, this method is expected to behave better compared to a single activation of the smoothing idea. The above process assumed that we know how to solve the smooth P0 problem. So how should this be done? Among the various methods that exist for this task, let's discuss a method known as the iterative reweighted least squares, IRLS. We choose to focus on the IRLS due to its simplicity and elegance. The core idea is very simple. We shall take the smooth L0 norm expression and turn it into a weighted L2. This is done by observing that every rho alpha of an entry xk can be rewritten as rho alpha of xk divided by the squared of xk, and all this multiplies xk squared. This modification is of course trivial, but now comes the punchline. We shall refer to the yellow term as given and solve for x with these weights considered as fixed. Here is the IRLS in more details. This is the problem we aim to solve, and as already mentioned, the yellow term will be considered as fixed weights computed from the previously held x. Thus, this is a simple weighted L2 minimization subject to an equality constraint, a problem known to have a closed form solution. In the IRLS algorithm, we will jump between this solution and an update of the weight matrix. Here is a block diagram describing this process. We initialize the algorithm with 1s and compute the corresponding weights. Given these weights, we solve what we have defined as P2 of W. Armed with the new solution, we update the weights, and so on. This method is also known in the literature as focus algorithm. Just before concluding this discussion, we must mention the most popular relaxation method for L0. In fact, this relaxation has been already presented in this course, the L1. The idea is to replace rho star by an absolute value of x, which indeed leads to an L1 penalty. So the problem we named P1 could be considered as a relaxed version of P0. This relaxation option is known as the basis pursuit algorithm. The elegance of this choice is in the fact that the newly defined problem is convex, with all the benefit that it brings. Furthermore, this problem admits a linear programming form, which we know how to handle. The question that must pop to your mind at this stage is this. Fine, this is indeed a lovely relaxation, but why should we trust it to approximate the P0 well? This brings us naturally to the next discussion.